Okay, hi everyone. So today we'll be doing the next part of the geometric deep learning. So last week we ended on graphs. So just a recap of what we have last week. We basically have graphs being defined as this, the adjacency matrix and a feature matrix, which is like the input. And then you can build a graph based on this. The adjacency matrix is just either 0 or 1 based on whether there's a connection between the nodes. So like, for instance, node 1 is connected to node 2, node 4, 6, 8, 10, as you can see in this diagram here, like here. Yeah, so the adjacency matrix just defines the connections like that. And the feature matrix is just like a vector space representation of the input data. So as what Prof mentioned last week, indeed, the feature matrix can also be done for like tabular data. Each of these nodes may not be connected at all for tabular data, but they can take in, at each training sample, you can take in like a series of d-dimension vector for each of them. And basically you can then use some form of graph to do tabular data. And each iteration that you do has a data sample of d dimensions. Okay, so this was the recap. Graphs can also be permutated arbitrarily. And actually that is the strength of a graph neural network. Because of this permutation invariance, it enables a lot of functions to be able to be extrapolated to like other nodes in the graph without much changes or without any changes at all. So this arbitrary permutation is actually a strength of the network and helps it to generalize better, especially for cases where the node position, okay, doesn't matter. Like how the node connects with the rest doesn't really matter. You just need to like sum up the nodes of the neighbors into the graph. Like for example, convolutional neural networks is an example of that, where you just need to sum up the neighbors of your neighboring pixels. Yeah, of course, in a convolutional neural network, you also may want to take into account the position. So that is actually an extension of what we need to do. So using like graph neural network, you need to have some other coefficient for that. Okay, so the arbitrary permutation can be represented as a permutation matrix here, P, where you apply the permutation matrix before and after the adjacency matrix. So before it permutates rows, after it permutates columns. So later we have a slide to actually show what this does. So like over here, it permutates the first node to be the second node. So you can see in the previous slide, the node number 1 is now node number 2. Okay, but in general, the connection is still the same. So one can say that this graph here on the right and the previous graph here, they are isomorphic graphs. Okay, because they are the same structure, although they are labeled differently. Okay, so we go on to more math. Okay, in basically formalizing this graph. So the graph neural network can be said, okay, as what mentioned earlier, with adjacency matrix A and node features X. Okay, so this one is basically, there's this overall function fxa that takes in the input, which is the node features X and the adjacency matrix A. And this is supposed to be a permutation equivariant function. Okay, and this permutation equivariant function is constructed using multiple phi over here that takes into account the node itself, as well as the node's neighbors, X and U, okay, which is the one hop neighbors. Okay, there'll be a slide for this formulation later. So basically the graph neural network, you take this local representation. It can be like basically you take a node and then like maybe you sum up the neighbors nodes. That could be the phi function. It's just to like sum up the node values of your neighbors. Okay, and then you do that for every single operation, and then we will get fxa. Okay, so I just illustrate this here now, but later there will be a slide to actually formalize this. So your fxa can be basically is just a total operation of each individual node applying their own function to like maybe sum up the neighboring nodes. So like the first row in this matrix could be for node 1. And then you apply the same thing for node 2, node 3, and so on. So basically the graph neural network, you apply the same operation like over at this node, and then you repeat the same operation for this node here. And then after you repeat the same operation for this node here. So you can actually see it as like doing this part of the neural network here. And then maybe if I use a different color, like maybe orange, this node will be this line here in the graph neural network. So you can see that this function here is supposed to be permutation invariant in the sense that it doesn't matter what node takes, what is the node position that comes into the network here. Okay, so this is actually a way for the function to be very generic and still be able to like apply to all kinds of nodes that you add to the graph. Okay, so okay, this one I will explain more later, but this just to give you a flavor of what's to come. Okay, so a generic graph neural network contains this graph as a vertex, or rather nodes and edges. Okay, and then the edges are in the adjacency matrix. So this is what we have seen earlier. So if node I or vertex I and vertex j are linked, then the adjacency matrix will be 1. Or you can see in the previous slide, it will be a black square. If not, it will be white, a 0. Okay. So I hope this is clear. Yeah, move on. Okay, after all this math definition, then I will just pause for some quick questions. Okay, so this is the one hop neighborhood definition. So this Ni is the one hop neighborhood. One hop neighborhood basically means one connection away, one hop. So the one hop neighborhood is defined as this. N subscript I is basically comprising of all the node numbers of which the adjacency matrix is a 1. Either Ji or Ij is a 1. Okay, in a bidirectional graph, it doesn't matter which one it is, because if Ij is connected, Ji is connected. But you know, sometimes you want to do directed graphs, then it's either or. Okay, so this is the one hop neighborhood. Okay, and then there's a way to like get the features in the neighborhood. Basically, is the nodes within the one hop distance. So it's all the nodes xj, of which j is in the one hop neighborhood here. Okay, so for every node, what you will do is you will take the current node value itself plus the node features of the one hop neighborhood, and then you will pass this through a function phi. Okay, so earlier you saw that this function phi must be permutation equivariant. Permutation invariant, because it will be regardless of order of all these nodes here. Okay, I mean, if you go back to the diagram here, these are permutation invariant functions. It looks very difficult here, but actually, if you see the graph diagram later, it's actually very easy. Yeah, all this, actually graph neural networks, I think, will be quite key in the future, because a lot of key applications are already starting to use graph neural networks. Like, for example, AlphaFold uses graph neural networks to achieve state-of-the-art performance for protein folding. And there's also a lot of other examples in like biology, where you use chemical molecules and so on, or in a knowledge graph, I guess. Yeah. Okay, so we move on to permutation matrix. So the permutation matrix basically reorders the rows and the columns. So you can see that if we have a permutation matrix that is like having the, that has the ones individually like this, permutation matrix will basically just reorder the rows. So like over here, if we take this and we take this like that, you will see that if the one over here, we will just take this element over here. And then for the second line here, if you do the matrix operation, you will see that you will take this element here. And you can repeat that for the last two elements as well, like that. So you can see that simply applying this matrix at the front, okay, it's just a row reordering. Okay, then if we apply like the permutation matrix at the back, okay, over here we apply permutation transpose. Okay, but actually, if you apply permutation, it's the same as well. I mean, apply the P matrix is the same as well. It's just different ordering. So if you apply this at the back here, what you'll get is that you will do a shuffling of the rows here, the permutation of the rows here, if you apply the operation at the back. So that one, I leave it to you to compute. I will not be going through in detail. Okay, but the idea of this permutation matrix means that we can actually apply some permutation to our graph, okay, to construct a like slightly different graph, but actually it is semantically identical, because regardless of how you permute your nodes, okay, it does not change the connections. Okay, so what is permutation invariance and equivariance? So as what I mentioned earlier, if we permute both the rows and columns of the adjacency matrix, it amounts to PA/P transpose. Okay, the first one is for rows, the second one is for columns. Okay, invariance means that after you permute your, like for example, rows and columns, okay, the way you process your function will still be the same as though you don't permute it. So this is in the function phi. Remember earlier you have phi. Okay, we have phi xu and xnu. Xu is your original node itself, node u, and the xnu is basically the one-hop neighbors of this node, the features of the one-hop neighbors of this node. So this is actually invariant, okay, because no matter how you reorder this, okay, the way this function works is supposed to give you the same output. Okay, this is just characteristics of graph neural networks. If you want to inviolate this assumption, okay, then we will not have permutation invariance anymore in graph neural networks, but it will be sort of, I mean, a different kind of graph neural network without permutation invariance. But for most cases, this applies. Okay, this relation applies. For permutation equivariance, it means that when we do a permutation on our input features of the input as well as the adjacency matrix, what we'll get is the same as our original function, but you apply a permutation at the start. Okay, so this equivariance is given for this function f. Okay, and this is basically the main function of the graph neural network. So the next slide will show you the relation. So this big function f, this big function f will basically go through all this. So these are your individual nodes operate. Basically, at each iteration of your graph neural network, you do one step through, and then you basically apply this function here. So this function is the permutation invariant function that you do on that particular node itself. So like for example, x1, and then you maybe like if you want to take the summation of the values of the neighboring nodes, maybe you just take summation of x2 and x3. So that will be just that summation itself would be this function here. And then you just apply all of these operations concurrently for all your nodes, node 1, node 2, and node 3, or node n over here. And then you do all these operations together concurrently, you will get the overall equation of a graph neural network, where you basically go through each node and then you apply this permutation invariant function on each of these nodes itself. And overall, this function here is permutation equivariant, because if we were to permute this thing here, okay, it's the same thing as you permute this function. Yeah. So yeah, that satisfies the equation at the back. Okay. So yeah, that's it for the permutation invariant and equivariant part. I pause here for some quick questions. Okay, Dylan, what do you mean by the math doesn't look right?
Right. Could you scroll back 3 slides? Yeah, I know. So move 1 slide up. No, I'm looking for the one where you draw the, yeah, there. Stop. Back. Stop. Okay.
This one, is it? Yeah.
Yeah, I don't understand how you're saying this is equal. I'm assuming the dash means a don't care operator, right?
Oh, no, it's not
what
don't
it
care.
is.
So in math, when you do this dash, right, this means that this whole block here is x1. So it could be like maybe a series of numbers like 0, 2, 5, 1. Okay, and then because of the way you do this operation here, so like the first row you do this multiplied with this thing, right? So the first row, let's say the second row here is, for example, it's not don't care. Okay, this x just means that I span the whole row. So it's quite commonly used in matrix multiplication for math. Like, so let's say I have 2, 5, 3, 7 over here, right? Okay, Dylan. So if I were to take this times this to get my first element here, right, in the matrix, this element will just be 1 times 2. So this will be 2. So similarly, if I do the second part of the matrix multiplication, I take this line here, multiplied by this line here, right? So this one will be a 5. Okay, do I need to continue, or you understand already? Then like this line here, and then you multiply here, you get a 3 over here. Yeah, and the last one will be a 7. So essentially, you can see that if you apply this matrix here, it's essentially like swapping the rows. Then similarly for the second row, when you do it here, it's taking x4 because this one is at the bottom.
So you're saying it's okay, but then how is it equal then?
It's just a way of doing matrix multiplication. So after you do this matrix multiplication,
It's not a way of doing matrix multiplication. It is matrix multiplication.
yeah, it is matrix multiplication.
Yeah. So Dylan, I think your previous x1 is just notation to say I'm going to call that first row x1. That's it. It's a vector. Is that make sense?
Yeah. So Dylan, actually, you don't have to know the math too much in detail. You just need to know that this doing this matrix multiplication is the same as permuting the rows. That's all we need to know.
All right.
And then apply this operation transpose to the back is permuting the columns.
I think let's not do that. Let's not say you don't need to know the math. I think that mystifies it unnecessarily. This is just matrix multiplication, Dylan.
Okay, I can kind of understand now after the explanation how the rows are getting permutated, but I still don't understand,
yeah. What is it you don't understand? Yeah, try to articulate it. Yeah.
No, it's actually important because
how is this permute? So you said earlier this is local like neighborhoods invariant for permutation invariance, right?
Yeah, this one. Yeah. So
how
you
does
apply
this
to
fit in again? Apologies.
Okay, so basically assume that each node, okay, let's say you give each node an algorithm. Okay, we talk algorithms because you're more familiar with it. So the algorithm for each node maybe is just a summation of all the node values of its neighbors. So you can see in the summation operator, if let's say I do 1 plus 2 or I do 2 plus 1, the outcome will always be 3, right? So if we use an operation that is permutation invariant, that means like if you swap the order of your inputs, the output will still be the same. Then we have essentially have a permutation invariant function, which is essentially what GNN functions are. They are permutation invariant by nature of their design. It's either a summation operator, the maximum operator, or maybe the minimum operator. So all this, regardless of how you swap your inputs, it will still be the same output. Yeah, so this is basically for each function or each node, you apply this permutation invariant function to it. And overall, at the whole graph level, you apply this equivariant function to it, which basically, you have to see the next slide. Actually, is basically this thing here. Yeah, which basically concurrently you do all the node operations at one time, and then you put them all into a matrix. Yeah. So no matter how you permute your individual elements here, it's the same thing as me. So if let's say this thing here is already permuted. It's actually the same thing as me permuting this original function, because if you permute inside here, it's the same as permuting outside. Okay, yeah, that's just how it is. Yeah. So this is permutation equivariant. Okay, then I hope you understand this because yeah, permutation equivariance is the main thing for graph neural networks, powerful generalization ability.
No, wait, invariance is not that you apply inside and it's no matter what input you give to the function, it derives the same output based on the fixed adjacency, right?
Yeah, so equivariant here is defined as...
No, wait, so going back to the previous slide you showed, it's not like you apply an operation inside there, then it's akin to associative rule where you just extract the operator out, right?
It is okay to extract the operator out for this case, because if we were to take this as a permutation invariant function, okay, and we just do a permutation here, so we just treat like you permute the features, okay? So essentially, if we permute, like, let's say the features over here, okay, then actually essentially is permuting this whole thing here.
All right, because of the dash thingy you
because the x1, x2 will be done by the permutation function. So essentially it's actually the same as permuting outside.
Okay. I'm still a bit caught up on how this is how this
Actually,
is random.
I think maybe I should have said the permitting inside. Okay, maybe there's no permitting inside, or the P function actually applies on X directly, like big X. Yeah, so this small x will then be permitted based on this P function. So maybe this x1 will be mapped to maybe x4, x3, x2. It doesn't matter how it's mapped to, okay, because essentially all these functions will still output the same result as though in their original position. So like, for example, if this is x1, they'll be mapped to somewhere with x1 again. So the outcome of this will still be the same. So x1 output here will still be the same as the output x1 here. Okay, and now basically what this means that if you just apply this permutation operation outside the function itself, it's the same as applying the P inside this X here. Because if you permute this outside loop here, it's the same as permuting this inside X.
Oh, okay. Now I kind of understand now. So it's not saying that the output gives the same exact solution no matter the
output.
the output is a permutation of
Yeah, correct. You got
so
it.
you're preserving some structure by
Yeah.
having the output at least being represented in other forms.
Right.
If
So this
assuming
thing maybe get
okay.
mapped to here, but then the output is still the same. And then
Yeah,
similarly,
okay, thanks. I kind of get
this
it.
block gets mapped to here. Okay, good. So any other questions so far before we talk on like why this is important? Okay, so actually, geometric deep learning is a way of finding symmetries and invariants or equivariances in your data. Okay, and then expressing that into the structure. Okay, so that you can actually learn more with less. In some sense, because you remember my earlier slide, if you only have like one example, but you already know all the symmetries involved in the environment, essentially you can learn with one sample or you can learn with one label. Okay, so of course, this will not happen in real life. What will happen is that you can actually drastically reduce the number of samples needed if you can imbue the right invariances or equivariance into your network structure. And it just turns out that graph neural networks are quite generic for like many data structures. For example, grids, knowledge graphs, protein molecules. What is not good for is like maybe continuous structures like spheres. Then the one you might need to use like gauges or geodesics to like do it. So that one I will not cover through. But if your data points are like all discrete different points, a graph neural network actually can be one of the most generic structure you can use to represent your data. Okay, that's why we are spending some time to touch on graph neural networks, because I feel like this is like more or less the when you like generalize all your models, you end up with like a graph neural network for discrete data points. Okay. Right, so I just touched on some of the how a graph neural network can be used. I think I covered this before when I talked on neural algorithmic reasoning, but just for a recap. So imagine you have a certain node feature X and an adjacency matrix A for your graph neural network. You apply basically your function that you saw earlier, the function XA, which is the way to do the permutation equivariant function. You do fxa to your graph neural network. Okay, and then you will end up with a latent space here, H, which is like the outcome after like you do the summation of all your other node values. Okay, so this H here maybe is the result of the sum. Okay, so this is called the latent space. Okay, just a caveat. Okay, you can actually do this operation like n times. Like you can do it multiple times here, because like you can just basically do this operation one time. You aggregate the neighboring nodes. Then you repeat the same operation with the updated parameters. You can keep doing this again and again. So a graph neural network need not be just one time. It can be multiple times as necessary for your particular data type. Okay, so the more times you do, the more data you aggregate, because each node will then have information of, like you do one time, you get one hop information. You do two times, you can get actually up to 3 hops, because like your neighbors will get one more hop, then you get their information. Yeah, so it basically, if you do enough time, your entire graph will get the information of everything, subject to, of course, the bottleneck of your variable X, the dimension. Yeah, so that dimension will have like be the bottleneck for getting the information actually. Okay, so now we move on to like the latent space, HA. So there are a few things you can do for this. So one thing is to do node classification, where you just pass it through a function f, okay, like maybe a neural network or MLP or something, to do a classification. Maybe you have to classify whether this node is it connected to other nodes or not, or maybe you can do something like, is this node fully connected? I mean, there are some things you can do with this, like node classification. Or if it is like a knowledge graph, you can ask, is this person popular or not, or is this person age greater than 30, you know, that kind of thing. You can do something like this using node classification. You can also do graph classification, which basically takes in, based on again using a permutation invariant operator. Okay, we take in all the latent variables hi, and then you do a function on the overall graph itself. So you can then classify whether, you know, is this graph fully connected? Is this graph a benzene molecule? That kind of thing. So this can be used for that. Then lastly, there's another application that you can use, is you can do link prediction. So like maybe for AlphaFold, you can use this to check whether or not like there should be a connection existing between these two nodes, or like what kind of connection is it? Is it like what kind of protein connects, or what kind of interaction is that? You can use a link prediction, which basically takes in the first node hi, the second node hj. Okay, and I did not touch on this, but you can actually also have age information into your GNNs. Okay, but for the purposes of the earlier math, we actually remove this age. Okay, but if you put in the age, okay, it will make it more complicated, but it will still be permutation equivariant. Okay, so a link prediction basically just takes in the first node and the second node, and then maybe checks for something like what kind of connection it is between these two. Okay, questions? Okay, good. We move on. So this is basically, so I'll be presenting to you 3 different architectures of GNNs. So actually this is all from Peter Velikovic's slides on GNNs. And I think he summarized GNNs pretty well. Okay, so this basically says that permutation invariance, okay, is usually, okay, is normally done by aggregating features from the one-hot neighbors, okay, with some permutation invariant function plus. Okay, this, I don't know how to say this in English, but this I just call it plus. Okay, and before that, you can actually transform this function using a function phi. So you can think of it as transforming it to an embedding space. You know, like transformers, you transform the word into a semantic space. So this function phi is like a semantic space. Okay, then after that, okay, you can update your node through this function. Okay, this is psi. Okay, this is phi. Okay, through some function phi. Okay, so this is basically the permutation invariant function we talked about earlier. And then we can learn both psi and phi. Okay, and yeah, this is basically what a graph neural network is. Okay, if we talk about just the node relations. Okay, that was difficult to understand. So let's look at some diagrams. Okay, so first case, a convolutional neural network. Convolutional graph neural network just takes into account all the like neighboring neighbors here. Okay, and then what you will do is, okay, you will then weight it by certain coefficients. Okay, this can be like arbitrarily. These coefficients over here, actually, if strictly speaking, okay, if we were to have different coefficients here, then this will not be like permutation invariant anymore, right? Because if you weigh differently for each of the input nodes, the position actually does matter. So this is a case of the neural network where so if you talk about it like a CNN filter, maybe you want to have all this kind of coefficients here, where you basically bias certain positions of your neural network, like maybe top left, top right, bottom left, bottom right. So you can do like CNN filters. So that's why this called convolutional, because it is related to like CNN filters. Okay, if you set all these coefficients to be 1, okay, then essentially this will be the vanilla GNN, where you don't actually have a certain position of your nodes. Okay, so what you do is you take in the input features of yourself plus your neighbors weighted by some coefficient C. Okay, and then you put the permutation invariant transformation here. Okay, which basically uses like this kind of operators where it's like sum, max. Yeah, so over here, the permutation invariance lies here in this operator here. Yeah, but I would like to just argue that if you like put this C differently, okay, then what will happen is that you actually don't really have invariance in your nodes because it's like related to what node you actually apply to. Okay, so this is a special case. Okay, so this can be a subset of this. Okay, so attentional graph neural networks, basically instead of using this C, which is predefined, you do an attentional weights here that takes into account xi and xj, which is your original node and your neighbor node. You take into account some function here. Maybe you can do a dot product. Okay, if you do a dot product, then this, anyone knows if you do a dot product and you do an attention-based weight linkage, what popular architecture would this be? Okay, anyone heard of this architecture before? It starts with T.
Rhymes with Optimus Prime.
Yeah, so I think Dylan got it. So if actually you were to do like dot product of vector spaces, you will actually get a transformer architecture. So actually the transformer architecture is none other than an attentional graph neural network. Of course, with added features, but essentially at its backbone is a transformer architecture because its weights of the connection will be dynamically defined. Okay, it will sum to 1, the coefficients will sum to 1, but the linkages will be dynamically defined based on the vector representations of your original node xb and your surrounding nodes xu or xa, xb, xe, xc. So this is a transformer architecture. I will touch on this later in the next slides. Okay, but just to let you know that actually this is all very linked to like state-of-the-art architectures. This one, the left side here can be linked to GNNs. If you set the right coefficients, it can be GNNs. If you set the coefficients to be 1, then it will be a generic GNN, which is the vanilla one. This one is linked to transformer. And then this actually is a subset of this message passing. Okay, because over here we use like we only have the coefficients here defined by your nodes, right? In message passing, you actually have the function itself, phi, psi, xi, xj. You can do more than just a dot product. You can do summation, multiplication. You can do basically a lot of things over here. Okay, and then basically since we pass it through this permutation invariant function here, this thing is still going to be permutation invariant. Okay, of course, this permutation invariant is still like position dependent in terms of your nodes, neighbors. Yeah, it's only permutation invariant.
Phi is a matrix, is it a distance matrix?
No, phi here will just be like maybe MLP or kind of neural network to like transform your input vector. So if you think of transformer space, if you think of a transformer, this psi xj, this psi xj will be basically, you know, your one hot encoding for your words transform into word embedding space. This psi does this word embedding transformation.
So it's like a kernel function instead.
It is yeah, it's like a projection to a n-dimensional vector. Yeah, so you can also do a similar projection here, but in this case, you can do a lot more things. So not just related to just the coefficients, you can do a lot more functions that relate to both xi and xj here. So the message passing network is the most generic because it allows for the most flexibility of your functions. And indeed, most notable GNN architectures are actually message passing architectures. It's just that the earlier few architectures have their specific use case. So all in all, actually, if you just want to study one architecture for GNNs, you can just study message passing. Yeah, because message passing is the most generic. It encompasses everything else before that. Okay, so message passing, the thing is your input node and your neighbor node come together, and then you have a certain message. Okay, in this case, your message is this psi xi xj. So your message will be here. And then based on the message, you accumulate all your messages together. Okay, so this is so you accumulate all your messages together along with your original xb. And then basically you apply some permutation invariant function here. Yeah, that is message passing. Yeah, in actual fact, you know, GLOM, like I talked about GLOM earlier, GLOM as in the GLOM that Geoff Hinton was talking about. GLOM is a form of message passing GNN also, if you view in that form, because you actually take the messages from your nodes at the top layer, nodes at the bottom layer, and then you accumulate all together.
It's not a
Yeah.
GNN though.
Sorry, what?
It's not a GNN. It's just vector embedding in the modules.
Right, but it uses some form of attention. So in some sense, if you use some form of attention, it can be seen as like a kind of flavor of GNNs. Although the backbone itself is a CNN, but the way the nodes interact can be viewed as a GNN. Yeah, but that said, I haven't really heard much about GLOM, so I'm not too sure about its effectiveness. But I mean, we have all heard about transformers, so I hope this motivates people to see that actually GNNs are actually quite versatile. And
Actually, Chongmin, from what you described, I still don't know what's a GNN.
okay, which part?
I don't know. I see equations, but I have no idea what's a GNN. You can ask the rest of the people if anybody can answer that question. I'm sure you can, but if you want to get some feedback, I'm telling you, I honestly cannot tell you what's a GNN.
Yeah, but Prof, you know that GNN is linked by like the input features X and the adjacency matrix A, right?
Yeah. So are these your features? So is this what I'm looking at? I'm looking at
So,
one data sample.
What you are looking at here is how to process a particular node's features based on the neighboring nodes. And then you update your particular node.
So these are not the features then.
These are the features. Xi are the features, and this Xj are the features. Just that
we see XA, XB, XC, XD, XE.
Oh yeah, these are the
these
features.
5 features.
These are the features of your neighboring nodes. Each of them have D dimension.
Well, that's different from what we discussed last week, which was that
each of the X is 1 pixel, right?
Yeah, this is one sample. And from what you're saying now, this is not one sample, this is no,
this is one sample. So basically a one sample, you interpret that one sample. It's like passing this, you can treat this D dimension as like maybe a single pixel of your image. And then you just pass this through your network to like do a CNN filter. And then at the end of it, maybe you do some softmax loss, right? You do some cross entropy, right? So that's for one sample. So you then do multiple samples in order to like tune the network. So at each iteration, this XA, XB, XC, XD, or this are all just like the pixels of that particular image of that one sample. Okay. So indeed, what you see here is just a graph for that one sample itself. Then you just iterate over many samples in order to do some batch training to train the functions here, to train these functions, phi and psi. Yeah, so it is like quite similar to a CNN actually. If you look at this left side here, like over here, this basically just training your filter weights. Like your psi here is a projection of your filter weights.
Yeah, I mean, it's a little bit confusing because in the CNN, your image is separate from the neural network architecture. So am I looking at the image here, or am I looking at some learning architecture?
If you were to take this as the image itself, then this will be all pixels. So this one will be a pixel value from 0 to 255. So you are looking at the micro interactions between like a single pixel and its neighboring pixels.
Okay.
Then why is it D dimension?
D is generic. So if you talk about like you want to treat this as a CNN, this D will be equals to 1. But of course, you can use this architecture can be used for higher dimensional data. I mean, even for CNN, you have 3 channels, right? So this D can be 3 if it's 3 channel. If it's a color image, then you have 3 different pixels for red, green, and blue.
So just to set the record straight, each of the nodes in the graph is just depicted as one sampling you use in your machine learning architecture. If
yes,
you use it for a pixel, it's just one, which is that pixel. If it's, for example, if you're smart enough for tabular data, you group some things in one capsule, and then that's your D dimension pixel in there.
Yeah.
Okay.
I have one question about the filter. So I'm looking at a computational GNN as well. So the coefficients correspond to filters in the CNN. So can I say that they are not necessarily scalar? They can be a vector as well. to represent multiple filters?
Usually this is done with a scalar coefficient. So it's like feature, like it's like pixel importance.
Yeah, I understand, but I'm just trying to see
Like
how this relates to a GNN.
In a GNN, this will be like 1/8 or 1/9, because like each of the pixels will be treated equally. You just need to multiply by a certain filter function, right? And you can map the filter function using this.
Yeah, I understand. But if you want to translate this to a CNN, right, then you should have multiple filters and multiple layers. And I don't see how this structure can handle that in that case. How would you represent multiple layers of a CNN like a ResNet in this kind of GNN structure?
Wow, they're talking about quite advanced architecture. Yeah, so if you want to do ResNet, you have to
Because this looks like one single layer.
Yeah,
one filter.
You have to build on GNNs as one block here, and then you do your ResNet as a meta unit of that GNN block.
Wow.
Yeah, so this does not have skip connections here. It's a different architecture.
So you're saying that this is like one layer.
This is like applying one filter to it. Yeah, this whole operation is like multiplying the image by that single filter.
And let's say we have multiple filters,
and what you
is equivalent to
you need to have
multiple GNNs.
Psi here, this psi here. Yeah, you need to have like psi 1, psi 2. Yeah, then maybe you have like multiple GNNs, and then you like sum up the results together. It's not. That's why this architecture was not meant to like replace CNN. It's just that we can view CNNs, like the basic operation of a CNN filter. If you were to like treat each pixel as equally important, and then you just basically map in the filter weights, like some form of bastardization, or you map in the filter weights here in this learnable function psi, you can view it as a CNN. Yeah, but of course, people don't really use GNNs to do CNN stuff. It's quite different.
Yeah, I'm seeing this as not very computationally efficient, because for CNN you can do linear algebra and S matrix multiplication.
That's correct. So
yeah, but
you have highlighted a very important part of GNNs. It is not very computation efficient. And that's because of our current hardware. Our current hardware does not support this kind of invariant operations very well. Like although you do it concurrently, but there's no vector here, there's no matrix here. If you were to use like CNN, you can just do a single one matrix multiplied by another matrix and you're done. Yeah, but over here you cannot do this, okay, because you need to do this separately for each node. Yeah,
it's like a for loop, right?
Yeah, it's a for loop.
Yeah.
Yeah.
For loop.
Until the day that people have implemented architectures or hardware architectures for GNNs, it will still be less efficient than CNNs in terms of hardware.
We got it. Thank you.
Any other questions so far? Prof, are you okay with the explanation?
A bit, but it seems a bit.
No worries, Prof. I understand, because I did not have a work example here, and I mean, if you're interested, I can talk more about it next time. But focus.
I'm just saying, it seems a bit. This just seems a bit contrived.
Yeah, the focus of today is just to show you that there's actually permutation invariant, equivariant here, and yeah, basically all this invariance, equivariance, all this can actually help with learning. Yeah, that's the main message for today. Yeah, so actually, if you use a graph neural network, it can extrapolate to multiple inputs very well. As I said, like if you train a neural network to sum up 3 numbers, if you were to include a 4th number in the test set, the neural network cannot work because it has not been trained on 4 numbers at the same time. But a graph neural network, you can just add in one more node here. And because if let's say you do the summation operator, okay, it's easily extrapolatable to a new unseen node. Okay, that's why GNNs are quite powerful. Yeah, in terms of like being able to handle dynamic data sizes. Because the base operation here is the same. Okay, I think I will move on, okay, because I want to give some time for leeway. So any other questions, feel free to just put in the chat, I guess. Yeah. So let's move on. Okay, I have a few more slides. Okay, so as I mentioned earlier, the attentional model can be viewed as a form of transformer. Okay, so this is quite cool because for the first time ever, you don't have to learn your adjacency matrix from your directly from handcrafted rules. You can learn it from your data. And that's also why transformers are like rocketing the whole place with like NLP. They also vision transformers, although I'm not too sure whether it's good because I think CNNs are still better for representing pixels. Okay, but transformers, they have this structure whereby your linkages between the nodes are defined using a softmax of the features itself. So this means that the network will pay attention to the nodes that are more similar to it than nodes that are not similar to it. So this is the attentional flavor. And you can see over here, this can be done like using self-attention, or like if you encoder, decoder attention. All this can be done. And all this will be constrained in the range 0, 1. The summation of all your linkages here. Okay, let's say we call this alpha 1, alpha 2, alpha 3, alpha 4. The summation of all your alpha, okay, must sum up to 1. Okay, this is the requirement for the softmax. Okay, but of course, this is not a hard requirement. Your this one can be any number actually. Yeah, but for the case of transformers, these numbers all sum to 1. Okay, because of the softmax function. Okay, and you can view it as like varying attention on your neighboring nodes. What are these nodes then? These nodes in attention, these nodes in transformers for NLPs, they are your various words in your sentence. Like the cat is sleeping. So then, like, let's say if you look at like cats, okay, in the embedding space, okay, after you apply this function to transform to the word embedding space, cat maybe attend to sleeping more than the rest of the words itself, okay, because of the way it learns the data. Okay, so it's quite cool. Basically a dynamic graph that is defined on the word vectors. But for this to work out well, you need your word vectors to capture the right semantic space or the right manifold. If not, this would be a disaster. Okay, so if you try to use this on tabular data with if you try to use this on tabular data without the right encoding, okay, you might actually get a worse performance if you use attentional based methods like this. You need it to be in the right embedding space. So if you can find the right embedding space for tabular data, I think TabNet tries to do that. Okay, but if you can find the right embedding space, it will work so much better. Yeah. Okay, Xiu, you mentioned now the H in GNN becomes the key in the transformer. What do you mean by that? Could you explain?
Oh yeah, it's just because now the alpha value actually is kind of telling you how important the neighbor is to you, right? It's just equivalent to the key.
Oh, you're talking about this,
yeah.
this being the key.
Yeah, yeah.
Okay, yeah, it is basically how much focus you want to pay to that word, right? So in some sense,
yeah.
it is. Yeah,
yes.
correct. Yeah, that's exactly the right way to view it. Although there can be multiple keys if you pay attention to more than one word or more than one vector, more than one input node. This key itself is not limited to just one node itself. If you understand what I'm saying, you can pay attention to like more than one neighbor value. Like cat can also pay attention to the. Yeah. So I prefer to call it attention because key, I will view it as just only one. It unlocks one door. Yeah. But in this case, it can unlock many doors. Is that okay, Shu?
Yeah, I'm fine. Yeah, just some general comments. Yeah.
Yeah. Anyway, I think you're also quite interested in GNNs. So yeah, it is quite a big field of research right now. So if you all are interested to do it, I think it's a quite good time to get into it. Yeah. Okay, so just a slide to just end off, okay, for transformers. Okay, so transformers, okay, you realize that because we talked about permutation equivariant earlier, right? So how does transformer put in the positional information of your words? Because sometimes your sequence matters. If not, you'll be viewed like maybe as a backup words, like I am not happy, you know, that kind of thing. All this, like I'm happy, I'm not happy, all this may not be given in the right order. It will just be viewed like all as one jumbled mess because of permutation equivariant. Okay, your input features can be permuted arbitrarily and then the output will still be the same, right? As we learned in the earlier slides. So in order to do that, actually transformers did quite an innovative method. They basically use positional embedding. Okay, this segment embedding is for segments for the sentences. This was done in BERTs, like first sentence, one embedding, second sentence, another embedding. So people have done this to basically imbue some form of position, okay, into the nodes itself. So over here, like this is your nodes xi. Initially, it did not have any of this information, but if you imbue these positional embeddings into like a d-dimensional vector, the same embedding as your word embeddings, essentially what you do is you imbue in the positional information into your input. And that is basically quite another way to get invariances. Or in this case, if you want your model to separate between the position of the word, all you need to do is to put it as an input to your network, which is quite something that I've seen a lot in a lot of modern architectures. They basically put the thing that they want to vary as an input. Like for alpha code, they put in, like, if you want your program to output C++ or Python, they put their language C++ as part of the input to the network. And I've seen that done in quite a lot of new models now. So this is like quite the norm nowadays, like this kind of putting what you want to vary in the input. Okay, so this just to complete the section on transformers. Questions? Okay, good. So actually I did have some slides on LSTMs and RNNs, but I won't cover that today. Okay, but basically the idea is that they are a form of a time warping invariance, which actually to me is quite nonsense. Okay, it just means that if you were to warp the data such that you sample at different intervals, your output might still be the same. Okay, but you can just treat it as RNNs or LSTMs don't really have much invariance because yeah, it doesn't really satisfy much of the symmetry criteria. Okay, if you are interested, I have the slides in the PDF, but I won't be covering that today. I don't think it's very important. Okay, we end off here with the final section. Okay, we should take about only 1 to 2 minutes or maybe 5 minutes. Okay, on reinforcement learning. Okay, how all these equivariance, invariance can be applied to reinforcement learning. Okay, this is something quite cool. Okay, so a rough trend of reinforcement learning is like this. Let's say, okay, this is the ImageNet. Okay, the number of samples needed to like classify ImageNet properly. Okay, then you can see that this is like over here. You can see this is like the supervised learning, right? So this is supervised learning. When you go into the RL domain, oh my gosh, look at this. If you thought supervised learning takes a lot of data, I can tell I'm a victim of this. RL really is a high compute industry. Okay, so in order to do RL efficiently, or rather in order for the algorithm to even learn like AlphaGo, AlphaZero, the original architecture took like over 1,000 GPUs. But of course, AlphaZero, they made it work on 4 TPUs or a single TPU. I think a single TPU over one day. Yeah, but RL is definitely very data hungry. So the real world can be similar like that. If let's say you want to do a robot put in an unknown environment, you might also have a requirement for large data. Okay, but you can actually drastically reduce the data if you can exploit some symmetries in the data. Like for example, equivariance in a Pong game. Okay, if you flip the screen, okay, is essentially the same action, right? It's like player 1, player 2. Whatever action is good for player 1, you flip to player 2, is the same action for Pong. Same thing for like cut pole. Cut pole is that you need to balance this pole here. If you were to flip like the left and right, and then you show the image flip, essentially it's the same game, right? It's just like doing a mirror and then you flip the controls. Yeah, so this is the way you can learn. Like for one data, you can learn this case and this case. So like people also have done like color variants in terms of like in a game you do permute the color and stuff like that. So if let's say you were to change the color of the grid, okay, but the actions are still the same. Like your meeple needs to go from the top. This is called meeple. Yeah, from the top left to the bottom right. Yeah, you actually have the same actions regardless of color. So this is a color invariance. So basically, you do rotationals, reflectional, equivariant plus invariance in like maybe color. Actually, this can actually do a lot of good for you, even in images, because actually all these are image data, right? I mean, except for cut pole, you get the velocity of the pole, but you can also treat this as image data if you were to treat the pixels. So actually, a lot of this kind of equivariance, invariance can be done for images as well. That's why data augmentation techniques can actually help to improve generalization. Like if you do you do flipping horizontal, vertical not much, right? Because vertical sometimes you don't view the world upside down, but flipping horizontal, changing the color, changing the saturation, all this actually helps to imbue. But remember what I said in the previous lecture, in the previous sharing, okay, is that if you were to imbue this as data augmentation, the curse of dimensionality states that you will need exponentially many samples in order for the network to learn all this equivariance or invariance. It is much better if we can imbue all this inside the network itself, like via a filter. Okay. So yeah, so let's move on. Okay, so one way to do this is to basically use homomorphism. Basically, why I said you imbue like this kind of symmetries into like some form of filters in the network itself. Okay, and then we basically can map the same space, these two things, into the same output space. So you reduce the problem, and hence you can use fewer samples. They did not do this by data augmentation. They did this by filter mechanism. So without going too much in detail, down here is the algorithm: principal, proximal policy optimization, and actor to critic. Okay, so this one, actor to critic. Nowadays got A3C also. Okay, but I will not go in the details of this because this is not an RL talk. Yeah, of course we can talk about RL next time, but basically you can look over here using the equivariance filters. It learns like in half the time. Like over here is like 1/3 the time, and here is like 1/2 the time. Like this is the traditional methods. Okay, so you can see that it actually helps to reduce the data. And I think it's around the same. Like over here, two element symmetry group is about half, right? 4 element symmetry group, maybe about 1/4. 2 element symmetry group, maybe about half. So I guess the more symmetries you find, the less data you need by that magnitude of symmetries you can find. Like you can find 16 symmetries. I'm quite sure you need 16 times less data or fewer data to learn, which is quite intuitive. Yeah. So in summary, okay, so I conclude with this slide. The structure of the network itself encodes the invariances of how you process the data, or the equivariances here. Okay, and then basically you can also put this invariance or equivariance into data augmentation, but it is not sample efficient. It takes exponential in the number of dimensions. Okay, the number of samples needed. You can also encode these invariances as an input feature. So remember, you put positional encodings. You can also put that as an input feature. But again, because you put it as an input feature, it is not inherent in the model. You will need to give it the whole range of that invariance. Like for example, positional embeddings, you need to give the whole range of positional embeddings that you want. Okay, because if you don't, you may not be able to extrapolate. Yeah. So there's some issues with that also, but it's not as big an issue as data augmentation. Data augmentation, you will need a lot more samples. But if you input as a separate input feature, it will still be okay if you have the training set iterate over like the whole range of all these features range. Okay, then this is actually this whole slide I just came out of it, but I think all these points should be valid. We can discuss more later. This thing here is if you want to encode more invariances in your model will be less general. Okay, I mean that makes sense. If you encode like rotational symmetry inside your model or reflectional symmetry, then you cannot differentiate between like a left image or a right image because you can flip it. But because you encode these symmetries inside, you can learn with fewer data. So a case in point is like CNNs. You imbue like translational equivariance, but tabular data might not have it. So if you use CNNs on tabular data, unless it is also translational equivariant, if not, you will not do well in it. And yeah, lastly, this point was made also in the RL case. Invariances and equivariances help to improve model convergence because you can learn with less data. Okay, that's all for geometric deep learning. I hope this excites you all to explore this area. I'm going to explore this area also in my next few works because I think this is something that, well, I would say that it's not everything to learning, as what Dylan and I have talked about last time. Okay, it's not everything to learning. It just helps to reduce the number of samples you need for learning. Learning itself will require a separate architecture. But if you have a problem with many symmetries you can exploit, okay, or maybe you can find new symmetries, color symmetry or something, you can actually help to learn faster with less data. Okay, that's all. Thank you.